Welcome to topology class. Last class we have discussed about closure and some properties of closure operators. And we have shown that a closure is nothing but A union A dash. That is whenever A dash is a derived set. So from last class we got some idea about closures. What was that ideas? Defining closure of a subset A. Right? We have seen that first of all definition. A closure means set of intersection of all closed sets in X which contain A. Whenever A subset of some topology is given X dot, then only we are defining A closure. This was the definition we have seen. And next we have seen that closure operator. Closure operator. That means we are defining theta of A is equal to or C of A is equal to A closure. Right? Next we have seen some theorem, that is A closure is equal to A union A dash, where A dash is the derived set. And what do you mean by derived set? That is A dash is the collection of all accumulation points of A. What do you mean by accumulation point? A point is said to be an accumulation point of a subset A if every neighborhood of some point X will contain the points other than X from A. Then we will say that the set or the point X is an accumulation point. Next we will pass to a theorem. 2.10 theorem. For a subset A of a space X, comma, A closure is equal to set of all Y belongs to X such that every neighborhood of Y meets A non-vacuously. CUOUSLY, non-vacuously. That means every neighborhood of Y meets A non-vacuously meaning is this, that is set of all Y belongs to X such that if N is a neighborhood of Y, then N intersection A cannot be equal to the empty set. This is the meaning. So if N is a neighborhood of Y, then every neighborhood of Y should have non-empty intersection with empty set. So how to prove it? Proof. First we will take this set as some set B. Okay. So let B equal to set of all Y belongs to X such that U belongs to the neighborhood system of y, that is ny, implies, our condition is u intersection A is not equal to empty, right? So taking that set as B. Now our aim is to show that now we have to show that uh, A closure is equal to B, right? That is, we want to show that we want to show that B equal to A union A dash. Okay. Now we want to show these two sets are the same. So our usual method. Now let some y belongs to A union A dash. A union A dash. Now if y belongs to A, then there's nothing to prove, right? Then certainly every neighborhood of y, certainly every neighborhood of y meets A at least at the point y, right? So what you're having, this y belongs to B. If y belongs to A, then every neighborhood of y meets A also, right? So therefore we will get this y belongs to B. Now now if our y belongs to A dash, by definition of accumulation point, every neighborhood of y contains a point of A other than y, right? Other than y. So what you are getting is, therefore this y belongs to B because it is having a neighborhood which contain a point in A. So it will have non-empty intersection with A. So we'll get y belongs to A. So y belongs to B. This implies when you're taking a point in A union A dash, it is contained in B. Therefore, A union A dash is contained in B. Now conversely, we want to prove B is contained in A union A dash. Conversely, let y belongs to B. Okay, if y does not belongs to A union A dash, what will happen? Then y does not belongs to A closure, right? So x minus A closure is an open set, right? Which containing y. So x minus A closure is a neighborhood of y which does not contain which does not contain which does not meet A which does not meet A, right? We have taken y belongs to B. Now, if this y does not belongs to A union A dash, that means y does not belongs to A closure, right? So, what you're having is x minus A closure, which is, since A closure is closed, is open. Now, y does not belongs to A closure means y belongs to the open set x minus A closure. Since this is open, this is going to be a neighborhood of y. Now, will it have intersection with A? Since y you are taken in B, right? So, let us take intersection with A. So, A intersection I want to take x minus A closure, right? So x minus A closure means A intersection, I can write x minus A union A dash, right? So x minus A is there. So this is empty set. A intersection x minus A. So it is an empty set. So it does not meet A. But as per our definition, y belongs to B. What was the set B? B means those y we collected so that its neighborhood should have non-empty intersection with A. So which does not meet A we have got, which is a contradiction, which is a contradiction, which is a contradiction to y belongs to B. So what you are having? So B is contained in A union A dash. What that is? From these two facts, called this as B, and previously we have proved this one, called this as A. Now from A and B, what you will get? You will get A union A dash is nothing but A union A dash is nothing but B. That is A closure is B. That is A union A dash is equal to B, or A closure is equal to B. So we have proved that A closure equal to B. Now this we will use, where we are using this result means whenever we want to check some set, given set is dense in a topology or not. So it is will function as a checking tool. Checking tool uh, or checking tool to check whether a given set A is dense in X or not. Okay, so whenever a topology is given, a topology is given, and it has got a subset. Suppose this is going to be a subset A. We want to show, we want to check that whether A is dense in X or not. A is dense in X or not. So what we want to consider? So in order to prove that it is not dense, we want to check, or we want to get at least one neighborhood of some point over here X, one point over here X, such that it is having a neighborhood which is having non-empty intersection with A. Once you prove this, we can see that A closure is not equal to X or A is not dense in X. Okay, so it's a checking tool for proving something is dense in X or not. Okay, next we are having a definition. A set, let A be a subset of a space X, then its boundary, or another name for boundary is frontier. Frontier. Frontier is the set A closure intersection with X minus A closure. A closure intersection with X minus A closure, and it is denoted by delta. So we will use delta A, or another notation is f of A. So what this means? A be a subset of a space X, then its boundary is defined as A closure intersection with X minus A closure. So we want to find some boundary. Let us see how it's working. So first of all, we are having a topological space. Suppose I want to find boundary of a subset. My subset is this one is my subset. So I want to find the boundary of it. So exactly, you know, boundary means, see, this is the one I want to find, right? This is the boundary. So what I am going to do, first I will find A closure. So A closure means this set A together with this boundary will come. Intersection with, I will go for X minus A. So X minus A means these portions, right? Now take intersection with A closure and X minus A closure. So exactly you will get this one. That means when you're having A closure, means you will get the circular part with this boundary, right? Now X minus A closure means you will get you can say that this punctured plan, right? So I will get this portion. No circle will be there. Okay. So this is Z. Now we take intersection of these two means exactly I will get these two intersection. I will exactly get this region only, right? So I will get a region like this. If interior is not there, exterior is also not there. So this one, exactly this bound. Next we are having one more definition. Nearness relation. Nearness relation. See, this definition is not in your syllabus, but for going for the next concept, we need at least this definition. So nearness relation X is a subset relation on X is a subset N of X cross P of X. That is, we are considering the power set also, which satisfy the following properties. The following properties, which satisfy the following properties. For y belongs to X and A belongs to P of X, we are having a notation here. Y delta A means YA belongs to the set N and Y delta bar A, not A, implies YA does not belongs to N. This is our notation. Okay, for y belongs to X and A belongs to P of X, Y delta A means that this pair belongs to N, and Y delta bar A means this pair does not belongs to N. Now we are having the condition. First condition, Y delta bar of empty set for all Y belongs to X. Second condition, Y belongs to A implies Y delta A for all Y belongs to X and A subset of X. Third condition, Y delta of A union B implies Y delta A or Y delta B for all Y belongs to X and A comma B subset of X. Now the fourth condition, if Y delta A and A delta B, Y delta A and A delta B for all A belongs to A, then Y delta B for all Y belongs to X and A comma B subset of X. So this is the definition of, this is the definition of nearness relation. So nearness relation, it exactly says that a point is near to a set. Whenever we will say that a point is near to a set. First of all, we are having this subset of X cross P of X. We are taking a subset of X cross P of X. So the first element should be a point and second one should be a set. Okay, first element will be a point and second element will be a set. So that's why we are writing YA. If YA belongs to N, means YA belongs to Y is near to A. We can say that instead of delta, we can say that Y is near to A. Now Y is near to A means, see, Y belongs to A means Y is near to A for all. Either Y is a point in A or says that it belongs to the set N. Okay, YA belongs to the set N. Then we will say that Y is near to A. Now, second property, If y belongs to A, then y delta A. Third one, y is near to A. Y is near to A union B implies either y is near to A or y is near to B. Now, if y is near to A and A is near to B, then what will happen? You're having a point here, y. Here you're having a set A. Now this y is very near to A. Now every point of this set is very near to another set B. That's the meaning, right? For all A belongs to A delta B. So the points in A are very close in B. So the distance between or y and B are very near, right? So we can write it as y delta B for all y belongs to X for A, B contained in X. So just to study the definition along for nearness relation, and we can see how we can make this use to prove the other propositions in the forthcoming chapters. Hope you understood today's class. So I'm winding up the session here. Thank you for your patient listening. Thank you.